In this first video, I just want to take an opportunity to go through the rules for significant figures and how to use them in calculations with data. First of all, the rules for counting significant figures. Number one, the easiest to remember is that non-zero integers always count as significant. If it is a number and it is not zero, it doesn't matter where it is, it counts. So for example, in 43, there are 2 sig figs. In 282, there's 3. In 0.911, we start with the 9. That's 3 significant figures. What it really comes down to is zeros, and there are 3 different classes of zeros. Leading zeros are zeros that come before any non-zero digit. For example, that 0 in front of the 0.911 in the previous example. Those do not count as significant. So for example, here in 0.0025, the 2 and the 5 are significant. In 0.01, the 1 is significant. Another type of zero are captive zeros. Captive zeros are zeros in between 2 numbers that aren't 0, and those always count as significant as well. So in 2.003, the zeros are in between the 2 and the 3, which are significant. So all 4 of those digits are significant. Likewise, in 100.04, those zeros are captive zeros. They count as significant. This has 5 sig figs. Trailing zeros are zeros at the right end of the number. These are significant only if the number contains a decimal point. So, for example, in 1.00 times 10 to the second, there's a decimal point in the 1.00. This is put into scientific notation in order to show that those 2 zeros are significant. So all 3 are sig figs. However, if you wrote the same number, essentially, these are both equal to 100, but 100 without the decimal point, then only the 1 counts as significant. Alternatively, you could write the decimal point right here after the second 0. You could add that decimal point in there. That would show that both of those zeros are significant as well. Exact numbers. Many times calculations involve numbers that are not obtained by using any measuring devices, but by counting. Those are called exact numbers, and they don't count toward our number of significant figures in a calculation. So they're considered to have an infinite number. For example, 1 inch. If you're using 1 inch is equal to 2.54 centimeters, or in 1 foot there are 12 inches. Those are conversion factors. Those are not found, or they don't count towards significant figures. If you count 3 apples, for example, that has an infinite number. And 6.02 times 10 to the 23rd atoms would have an infinite number because that's a number that is devised by counting. I should say, however, if I go back to this 1 inch example, if there is 1 inch that was obtained by a measuring device, for example, you used a ruler to measure 1 inch, then it wouldn't have an infinite number. It's only if you were using that 1 inch converting as like 1 inch equal to 2.54 centimeters. Let me go back to this. The biggest time that this is going to come into play is with mole weights. Mole weights or molecular mass, formula mass. We'll talk about that more in a further section. But when we use mole weights are numbers that are found essentially by counting atoms, even though we don't physically do that. And so we do not count mole weights into our number of significant figures. Scientific notation. As a review, when you move the decimal point, you move the decimal point until it creates a number between 1 and 10. It can be equal to 1, but it can't be equal to 10, less than 10. So here you would move the decimal point all the way until it comes after the 1, 1.01. And if you do that, you move it 5 places to the left, so it's times 10 to the 5th. On the other hand here, you're moving the decimal point to the right. It's a number less than 1. It's a smaller number, so the exponent becomes negative. 5.2 times 10 to the negative 5th. This becomes 3.3 times 10 to the negative second. Again, you're moving the decimal point to the right. And here, you're going to move the decimal point 3 places to the left, 2.25 times 10 to the third. Again, notice all of these numbers are between 1 and 10. Some advantages to using scientific notation, also known as exponential notation. This, as I mentioned earlier, allows us to indicate the number of significant figures easily. It also helps us convert large or small numbers into something more usable. For example, writing 0 point, all of those zeros until we get to the 6 versus just writing 6.0 times 10 to the negative 11th. We have a smaller, number to deal with, even though value-wise they're the same. A third advantage, and I don't think I left a space for this in the notes, but a third advantage to using scientific notation is with helping with mental math. And this is going to be particularly important when we do the multiple choice section of tests where you're not allowed to use a calculator. And as a review, when you look at 0.00004 times 200, I don't know if I could do that. You're going to try and keep track of your decimal places, but it looks a little difficult. But if you put it in scientific notation, 4 times 10 to the negative fifth times 2 times 10 to the second, now we can remember our rules for multiplying and dividing in scientific notation. And that is, in multiplying, you would multiply these numbers, the 4 and the 2, the coefficients, and you add your exponents, the negative 5 plus 2. So the answer to this question is 8 times 10 to the negative third. The rules for significant figures in mathematical operations. When you multiply and divide, we look at the total number of sig figs. And the total number of sig figs in our answer would be the same as the number in the least precise measurement. So, for example, you have 4.56 times 1.4. If you do that on your calculator, you'll get 6.38. But our measurements, our least precise measurement is the 1.4. We only have 2 sig figs in that measurement, which means that limits our final answer to 2 sig figs. So the corrected answer would be 6.4. Addition and subtraction is a little bit different. The result has the same number of decimal places as the least precise measurement. Not the same total number of sig figs, but decimal places. So for example, if we were adding these 3 numbers, our final answer would have the same number of decimal places as the least precise measurement. This one has 2, this one has 1, this one has 3. Again, I'm looking at the number of places after the decimal point. If you do that on your calculator, you get 31.123. However, our answer is limited by this 1 place after the decimal point. So our corrected answer would be 31.1. Just a couple rules for rounding, and this should definitely be a review. In a series of calculations, we will carry the extra digits through to the final result and then round. So when we're doing stoichiometry, for example, and you're doing multiple steps, we will round our final answer to the correct number of significant figures. If the digit to be removed is less than 5, the preceding digit stays the same. For example, if I was going to round 1.33 to 2 sig figs, I would round it to 1.3. If it's greater than 5, then the preceding digit is, or if it's equal or greater than 5, then the preceding digit is increased by 1. So for example, if we were rounding 1.36 to 2 sig figs, it would be 1.4. Do not round sequentially. So for example, if we were going to round this to 1, this is a bad example for that, but you wouldn't round twice. And I can show you an example of that in class. We will stop there and move on to 1.2 later.